Welcome to this talk. It's titled Making Machine Learning Work for You, Approaches that Deliver Practical Business Value. This talk is aimed at tech leads and senior software engineers, or those with similar experience, who haven't made use of machine learning tools in their work yet. This will be our agenda for today. First, we will go through some interesting challenges that might be familiar with you that can be solved using machine learning. Then I'll mention some traditional and unconventional data sources before getting deep into two real cases that I worked with recently. We'll call them cache optimization and sales forecasting. While going through the solutions of both challenges, I will mention many technologies and techniques. So we will follow by making a quick data science recap, and then we will talk about how you can start using these technologies too. And finally, we'll have space for Q&A. My name is Emmanuel Byrd. I am a senior software engineer with a bachelor's and a master's degree in computer science, and I will guide you through this machine learning discovery. So let's get to it. When someone mentions machine learning, we can easily think of the latest trends: image generation, text generation, self-driving cars, or even playing video games with our minds. If we think about it that way, it feels a distant technology. It feels like it has to be a disruptive thing for it to be useful. And it certainly feels both out of the reach of engineers and not in scope for businesses. But I don't think that's the case. I think it can be applied to many businesses, and I think many engineers could get their feet wet with the technology without making a full career switch. Let me illustrate this with the following challenges. The challenges that I chose to share with you have many things in common. For starters, they don't need a cloud setup, at least not in the sense of an integrated service with our applications. The development, training, and execution can be done locally. They can provide one-time useful insights or information that is immediately actionable. And lastly, I think these solutions can be coded by a small development team, maybe even by a single experienced developer, let's say a senior software engineer. Given that scope, let's look at what we can do. One of these challenges is anomaly detection, which we can use to identify the odd one out, to identify anomalies or outliers that indicate unusual behavior or potential issues. This can help in detecting fraud, monitoring system performance, or identifying anomalies in network traffic. Or sales forecasting, a well-understood challenge in businesses. A developer can create a predictive model to forecast future sales. We'll see an example of this later. This tool can help in planning inventory, managing resources, and optimizing production. Or performance optimization, a headache for large companies. Using different tools, we can potentially identify bottlenecks, optimize resource allocation, and predict system behavior under different scenarios. Pushing our limits and understanding a bit further, what about bug detection? We could potentially identify and prioritize software bugs by analyzing code repositories, bug databases, and observability metrics. And last but not least, the yet again well-understood challenge of customer segmentation. A developer can segment customers into distinct groups for targeted marketing campaigns or personalized recommendations. All of these challenges can be done with the limitations I mentioned in the beginning. A small team, or even a single developer with no cloud infrastructure who creates actionable information. The developer would, of course, need the data to start working with. Talking about data sources, which data you need depends on the problem. Let's look at some data sources that are very likely to be available for a vast number of organizations. It is intuitive to think of our data sources in terms of logs and databases, maybe also sensory data if the business has sensors like temperature or even mouse clicks. Or we can use public APIs that can provide the information we are looking for. But there are more data sources at our disposal that we normally don't think about. With recent advancements in natural language processing, we can use unconventional data sources like bug reports and customer support tickets to feed our machine learning models and processes, or user feedback and user activity logs. We can even start using version control systems to understand and map intentions of previous commits, unfinished changes, repeated libraries, or unresolved to-dos. And with machine learning too, we can start addressing them easier. Tools like ChatGPT and GitHub Copilot can drastically increase the performance of developers, helping them keep consistency of style, patterns, rules, and a much better exploitation of the available dependencies, of course, to be used with care and discretion. To illustrate some challenges that engineers face constantly, but very rarely solve with machine learning, I would like to rely on a couple of recent and real experiences of mine. In a recent engagement, I was working closely to a cache and all its challenges, basically trying to figure out how we could make it work better. In this engagement, the keys of the cache were file names and were composed of a type and an ID. The type can be either buyer or seller, and the ID is an arbitrary string. The cache sits in front of a cloud bucket. If the file exists in the bucket, it returns an HTTP status 200, and if it does not exist, it returns 404. What the system does with that information is known by a different team. Requests that are repeated are served from the cache, preventing unnecessary access to the bucket. So in our situation, our cache was missing too much, and we didn't know why. We changed its size multiple times, and it didn't fix the problem. So we realized increasing its size further wouldn't help. It was intuitive to think that maybe we could intercept traffic before it arrived to the cache, so that the cache only remembered those requests worth remembering, and thus optimizing its usability. In other words, making its life easier and taking less memory in the process. So my goal was to find requests that had the same characteristics and would always create the same result. Because if the answer is always the same, we don't need to ask the question. I chose to use a decision tree for this task. And this is how I wanted the solution to look like. In my perfect solution, many requests would fall in every category, and every leaf would have 100% accuracy. For example, going through the upper path, if the type is seller and the ID is numeric, the HTTP status would be 200. I wanted to find something like this. So I used a decision tree classifier from scikit-learn to build it for me. After pre-processing the record of requests in a format that could be used by the classifier, I ended up with a tree too big to provide actionable data. And the leaf nodes were not even 100% true. This resulting tree had 5 levels, so after making 5 decisions, there was still some error in the prediction. This didn't work for me because I needed characteristics that I could turn into code. And for that to work, it needed to be 100% true all the time. Figuring out that the previous approach was not working quite accurately, I looked for an alternative. I explained my data and goal to ChatGPT, and it suggested a tool that I didn't know. At first, I avoided it because I didn't want to deal with learning something from scratch. But after realizing there was something off with my approach, I decided to give it a shot. ChatGPT's suggestion was something called the a priori algorithm. It finds relations of different features in the data. What does that mean? If your data has multiple features or dimensions, it will create groups using some common characteristics and search the characteristics that are prominent within the group. For example, these figures have one color and one shape, so 2 dimensions. If we group the triangles, there is a high chance that any of those figures will also be green. Or if we group red figures, there is a high chance they will also be circles. So again, I pre-process the data as needed. I ran the algorithm with my data, and I chose to only keep the rules that were 100% true. I finally removed the redundant rules, and lo and behold, all of my questions answered. I found many different characteristics that always returned a status 404. That means those files were never found in the system. In these results, which is a representation of what actually happened, those files with type seller would always return an HTTP status 404. The same thing with IDs that were non-numerical, mean IDs that have letters or symbols. and IDs with lengths 1, 2, 8, and 9. All of this means that for a file to have a chance of existing in the cloud bucket, it needed to be of type Byrd, the other type, to have an ID that was numerical with a length between 3 and 7. And I think that is crucial information. It means some process in the system is constantly asking for files that do not exist. We don't know the implications of that. Is it then trying to create the file? Is the creation of such file even succeeding? Is creating the file expensive? Is it searching in the wrong bucket? Is it waiting needlessly while checking? Finding something that fails 100% of the time is always a red flag. So I communicated this information to the team and continued designing the cache. After filtering the requests with the previous information, I still needed to choose the appropriate size of the cache in terms of maximum items and expiration time. Making it too large will consume too much memory, but making it too small will limit how useful it is. Getting the right balance is not a trivial question, especially because you can only measure the performance of the cache after observing its behavior, after trial and error, or after simulating it with historical data. In this case, the given record of request spanned 3 days. So I created a simulator to read from it, to simulate the passage of time, and to show me how the hits and misses would have looked like for those 3 days. I could change the size of the cache at will and run the simulator again to get a different result. Having the simulator in place, the challenge now becomes finding a configuration that maximizes hit ratio without compromising memory usage. In traditional programming, you would define a search space and go through every single possibility, evaluating the cache and measuring its result. Only when you finish could you choose which combination was the best. If every evaluation takes, say, 5 minutes, evaluating all of them becomes impractical. What if you have thousands of different combinations? Or what if you reduce your search space, but leave out the optimal solution? There was another approach I could take. In machine learning, problems of this nature are called search problems, and there are many different ways of approaching them. I chose to use one called Bayesian optimization, where you start with the same search space, but only a small set of points to evaluate. The algorithm is very useful when computing the score function is expensive or time-consuming, as it was in this case. It uses probability to estimate which new point has better chances of scoring higher. It iterates over their results to find a very good answer. In this cache optimization case, it estimated which point had a better hit ratio without compromising memory. You can use this approach to search parameters in functions that are too expensive to evaluate or take too much time. For example, searching optimal configuration for things like connection pools, memory sizes, number of instance replicas, garbage collection settings, load balancing settings, you name it. How much could we improve our systems using the data that we already have and some of these tools? How much more efficient can we get if we let machines do the searching for us? Let's look at one last challenge with a different nature, one that humanity has dreamed of solving for ages, predicting the future. Forecasting is the art of using past data to predict future data. The nature of time passing creates a sequence of data points that can be used to predict future data points. How does this relate to your system? For example, if you could know how much user traffic your application was going to have in the next hours or days, you could upscale or downscale the system to properly meet the demand. The better your prediction, the better the use of your resources. The system never overloads, and the computers are never idle. To illustrate it, let me use a simple example of monthly sales through 10 years. We can see the data is cyclic, and it follows an upward trend. In this example, I used a toy dataset. but the implementation to get the prediction in the real scenario was mostly the same. I used an open source library called darts to make the forecast. In this chart, the blue line is a prediction. And I think it looks so good that it seems fake. It took me around 10 minutes to build the code that make this prediction. Yes, this time it was an educational dataset, but the ease of use holds. And you might think it surely can't be that simple. It is. Here's the code. I create a time series, split the datasets, create the model with default values, train it, and ask for a prediction. It doesn't get any simpler than this. When using the library, I get the same feeling as when I am using Rails or Express or React. When I first start using those tools, I don't really understand what's happening. I can still create a website though. I can really understand the whys and hows only after some time using the tools, digging deeper and reading documentation over and over again. Still, on day one, I can have a website running. So if most of us started our software development career the same way, why should machine learning be any different? Talking about libraries, so far I have presented many machine learning concepts and tools that might be new for you. So let's make a quick recap. It's only fair to give credit to those that make them easily accessible. First, I use the decision tree classifier of scikit-learn when trying to get insight from the cache keys. I realized my approach was off, so I used the a priori algorithm for efficient a priori in my second and successful attempt to get insights from those keys. Then I used Bayesian optimization from scikit-optimize to find an optimal cache configuration. And I used exponential smoothing from darts to get time series forecasts. There are many other packages, libraries, modules, and tools out there for similar and much more different problems. The tools vary in how much control you want to delegate to default values and processes versus how much you want to do by yourself. Of course, with more power comes more responsibility, but there is something for everyone. Navigating through the web to find the right tool for the job is part of the challenge. So where would you start? I mentioned at the beginning of this talk that this could be achieved even by a single developer. If you don't know these tools or concepts in advance, how do you make the first step? Well, the answer is yet again, machine learning. These GPT technologies become better by the week, and I have found them to be really good at answering machine learning questions. So open your favorite non-human pair programmer and throw your wildest questions at it. If you can explain the information at your disposal and your goal, you have solved half of the problem. Let ChatGPT give you educated direction to solving the rest. Learn a little through each interaction and allow compound interest to work its magic. This is a technology to use with care. And if you prefer not to use them, traditional web searching is a great option too. The principle of doing research and gathering knowledge is certainly something we are familiar with. Once you have a good enough solution for understanding the problem and a good enough plan, follow it through. Worst case scenario, your approach will be wrong, like I was with the decision tree. You will still learn something along the way. Most machine learning solutions work the same way. They provide good enough answers and very rarely a guaranteed best. They still work and they still work really good. So let's use the same spirit and aim for something very good, but not perfect. Iterate on your solution and it can only get better. Lastly, of course, have fun, discover the magic, and discover that behind it, there is code, yes, some math, but also many libraries for every taste. Of course, you'll have to look for answers, but chances are you are already doing your research in your current role. None of these concepts are new to you, and they are nothing you can't handle. So here I am, doing my best in hopes that you get out there and make the magic happen. But what do I get in return? Hopefully, collaboration. My hope is that if you start using these technologies, eventually we will work in a group where I can ask a colleague some machine learning questions, and perhaps one of them can ask me something that makes me wonder and learn. Maybe together we find the bug in one of these libraries, and perhaps we can contribute a solution to fix it. Remember how I previously mentioned to use GPT with care? Maybe we can start joining the conversation on how to properly use those powerful tools to get all of the good and none of the ugly. And my bet is you can do all of it without doing a full career switch. After all, this technology is and always has been at the tip of your fingers. So that's it. Thanks a lot for your attention. I hope you give it a chance at incorporating these technologies to start solving challenges that you are probably already facing.